Welcome to the Church of Perpetual Life live stream. Tonight, January 12th, we are celebrating James Bedford Day. On this day, every year, the city of Hollywood, where we are located, has a proclamation to state that the city recognizes this day to be a celebration of James Bedford, the first person to be cryopreserved. I'd like to bring an article that was recently published to your attention, an article from Fortune magazine. It was in our newsletter from the church that went out earlier this week, and the writer suggested that President-elect Joe Biden create an Operation Warp Speed to stop biological aging. It's an amazing article, and if you would like a copy, please send me a message. I'll get you a copy. And this is one more good reason to make sure that you are signed up for our church newsletters. So if you do not currently get them, let me know and I'll make sure that you do. You can sign up for them easily on our website toward the bottom of the page. Before we begin our program, I'd like to let you know also that the Coalition for Radical Life Extension is having a free online seminar on January 23rd. It is called Eyes on the Prize. The smart way to stop sickness is to stop aging. James Stroll and Bernadine will be hosting 3 great speakers on January 23rd. They are Dr. Amy Doneen, who will be speaking about heart attack and stroke prevention, Dr. Jason Williams, who will be addressing next generation oncology through immunotherapy, and our own Bill Falloon will be giving an update on age reversal. Just go to the Coalition for Radical Life Extension website and register for this event. Please send me a message if you need any help. Our next regularly scheduled service, our monthly service, will be on January 28th, Thursday at 7 p.m. And you can find us through our live stream. The link will be on our upper left-hand corner of our website. And this service will be a much needed age reversal update from Bill Falloon. So now let's go to our main introduction from the church itself. Welcome to the Church of Perpetual Life. My name is Neil Vandery. I'm your officiator here at the church. If this is your first time joining us at Perpetual Life, I'd like to invite you to join our email list so that we can get you updates on all that is going on with Radical Life Extension and so that we can let you know what's going on at the church. You can join our email simply by sending me a message at neil@churchofperpetuallife.org or send me an email through our website at perpetual.life. I understand that there are many people all over the world and all over the country creating watch parties using these presentations for their presentations, and I would recommend that you can also use our YouTube recordings as well. I'd like to invite you to have events like that in your communities. So often I'm contacted by people that say, is there a Church of Perpetual Life in their area? And no, there is not. This is the only one in the world. So join us. Luckily, we do live stream our presentations and we have these recorded. So join us here. I miss you. I hope that we can get back to meeting in person. When COVID-19 passes, then I look forward to doing that. Please join me while I recite our creed. We believe that all of life is sacred and that we have been given this one life to make unlimited. We believe in our Creator's divine plan for all of humanity to have infinite lifespans in perfect health, eternal joy, rendering death to be optional. By following our gospel, we achieve eternal life, creating a heaven here on earth. We also follow Nikolai Fedorov, who taught that the transcendence of the Creator will only be solved when humanity and our unified efforts become an instrument of universal resuscitation, when the divine word becomes our divine action. We follow Arthur C. Clarke, who said, the only way to discover the limits of the possible is to go beyond them into the impossible. And so we enter each day energized in spirit and empowered by the words of our prophets to live in joy, serving our Creator and all of humanity forever and ever. As you know, RadFest was this past October, and they had many amazing presentations at RadFest, which you can sign up for and see. if you just go to radfest.com, raadfest.com. Please be sure to share this event and this presentation, this live stream, with all of your friends and family, all of those that you love. Here at Perpetual Life, we follow the prophet Arthur C. Clarke, who said, when a distinguished but elderly scientist states that something is possible, he is almost certainly right. And when he states that something is impossible, he is very probably wrong. We also follow the prophet Nikolai Fedorov's philosophy of the common task for humanity. Fedorov believed, as we do here, that we should divert human energies away from wars and dissensions and toward measures for protecting mankind against natural disasters like floods and hurricanes and droughts, and especially aging, and to transform nature from a temporary enemy into an eternal friend. The Church of Perpetual Life is a transhumanist church. We are a science and faith-based church, and our faith is in the Creator and in the humanity to find ways toward a healthy, unlimited lifespan. Because of the COVID outbreak, we're not having any in-person meetings, so we invite you to join all of our meetings live stream until we get back to in-person meetings. I hope you enjoy this evening's presentation. I'd like to tell you a little bit about Ben first. His presentation tonight is Biotechnology in the Age of COVID-19. We'll get to your questions at the end of the presentation by Ben. Ben Best was president and CEO of the Cryonics Institute for 9 years between 2003 and 2012. Ben Best is a well-known activist in cryonics and life extension advocacy. He holds undergraduate degrees in pharmacy from the University of British Columbia and physics and computing science and finance from Simon Fraser University in British Columbia. Ben Best is also certified as a professional registered parliamentarian by the National Association of Parliamentarians. He currently travels around the world, attending age reversal conferences and meetings with researchers working to reverse human aging. Let's welcome Ben Best with his presentation, Biotechnology in the Age of COVID-19. Ben.
Anyway, I'm pleased to have this opportunity to, there's been a lot of talk about, you hear about COVID-19 all the time, but you don't often hear about molecular biology of COVID-19. So I'm pleased to be able to make a presentation about dealing with this subject that's too often ignored. That's who I am. And so just to remember what they were, the basis for this presentation is the celebration of James Bedford being cryopreserved for 54 years. He was a psychology professor, author of 7 books on vocational training, and at the age of 73, exactly 54 years ago, he was cryopreserved and or cryonically preserved, and he's currently in liquidation at Alcor. So this is the emphasis here is on biotechnology, molecular biology, as I said, and an overview. And but I know a lot of you are lay people, so hopefully intelligent lay people. And so I'm going to use a lot of illustrations, maybe make all these mind-boggling complex issues simplified, possibly oversimplified. Anyway, it's the biotechnology I'll be talking about will be mainly relevant to COVID-19. And I'm not going to be talking much about how to prevent COVID-19 or what the epidemiology is or a lot of other issues. It's all emphasis molecular biology. What is biotechnology? It's application of scientific and engineering principles by processing by and for biological materials. And its procedures for modifying organisms for human purposes. And includes genetic engineering, tissue engineering, stem cell formation, and such things as in vitro fertilization. So start at the very beginning. Our bodies are made of cells, and they're controlled by a nucleus, and the nucleus contains chromosomes that we inherit from our parents. And chromosomes are made of DNA, which codes for the genes. So we have what we call the central dogma of molecular biology, which is that DNA makes RNA, which makes protein. And proteins as enzymes determine everything that happens in the cell, synthesis of fats and other cellular components. Cells controlling the brain, kidney, everything, all of our organs. So here's another illustration. I'm going to use lots of illustrations to make my points clear. And another illustration for the central dogma. In this case, it shows that DNA uses an enzyme, a polymerase, to create RNA, but it also replicates itself during cell division. So there's an RNA polymerase and a DNA polymerase. And when we produce RNA from DNA, that's called translation and transcription. Don't get them confused. Okay, RNA from DNA is transcription. Protein from RNA is translation. So there it is, transcription making RNA from DNA and translation making protein from RNA. And some viruses actually can make DNA from RNA. And they use an enzyme called reverse transcriptase. And the HIV virus that produces AIDS uses reverse transcriptase to make DNA. So viruses contain DNA or RNA. So here's a picture of a bacterial virus. It attaches to the bacteria with its feet and injects DNA or RNA. And then the DNA or RNA forces the cell to make more viruses. It takes over the cellular machinery, so to speak. And then the cells the bacteria will burst, releasing more viruses, into the body or wherever else it can find other viruses. There's a lot of them, a lot of these things in seawater, actually. COVID-19 is caused by a single strand RNA virus, the SARS-CoV-2 virus, which is rather than being in that other kind of structure, it's in a spherical virus covered with spikes. And the spikes get into our cells by attaching to what's called an ACE2 receptor. And then once the spike attaches to the ACE2 receptor, the entire virus is brought into the cell. And once it's into the cell, the capsule gets degraded and releasing the RNA inside the cell. And then the cellular machinery uses the virus RNA to make more viruses, and they get released out to infect other cells. And so this ACE2 receptor is it's on the lungs, but it's on many other tissues. It enters our body typically through the lungs, but then it can go to the heart, kidney, liver, brain, etc. So it's once it has entry in the body, it can go to the ACE2 receptors on all these other organs. So it's not just a respiratory disease. Now, I want to make a distinction between antigens and antibodies. Antigens are the substances that are found on viruses or bacteria or whatever that cause an immune response. The spike is the primary virus antigen for COVID-19. And antibodies are substances produced by the body to eliminate antigen-containing substances. And antigens are detected by the immune system by antigen-presenting cells, which display those antigens on their surfaces to activate the immune system defenses. So that's what an antibody looks like roughly. And you see one of the arms, it's like the big slingshot. One of the arms it attaches to the antigen. And so we have what we call polyclonal antibodies. They're mixtures of antibodies which could be derived from giving antigens to animals or taken from human donors so that the animal or human antibodies can be given as therapy. Monoclonal antibodies are antibodies against a single antigen. So here we have antigen-presenting cells recognize the virus that contains the foreign subject, the antigen, in this case, the spike on the virus. And then the APCs recruit T cells and B cells to fight the virus antigen. So there we see at the top the APC recruiting both the T cells and the B cells. Now on the left, you see the T cells, and the T cells recognize the antigen on the infected cells because the antigen will be on the infected cells, and the cells that are displaying the antigen are what the cytotoxic T cell is trying to kill, is what they're attacking. On the B cells, on contrary, on the right-hand side, are creating all these antibodies. So we're fighting the infection both with the T cells direct attack and the B cells releasing all these antibodies, and also the immune system will release a lot of create a lot of inflammation, which damages both normal and infected cells. So these cytotoxic T cells, it just shows a picture here. They release these substances called perforin that makes holes in the infected cells, and then releases toxins to enter the holes and kill the cells. Now the antibodies prevent virus from entering the body. As you can see in this in the left-hand side, the virus attaches itself to the ACE2 receptor, but on the right-hand side, it can't attach to the ACE2 receptor because the antibodies are attaching themselves to all the spikes. So antibodies can be used as therapy. Recovering COVID-19 patients often generally have a lot of antibodies, so they can be given to new patients, and it's been shown to reduce the risk of disease progression by nearly 50%, according to this study. And whereas artificial antibodies, instead of having to take them from a patient, they can be engineered to have a high affinity to bind to the COVID-19 spike proteins. So another problem is all this massive inflammation that's caused. So we get the inflammatory cells secreting all these inflammatory cytokines. IL-6 is an example of one of them, but there's lots of inflammatory cytokines. So it's good in terms of the inflammation killing the viruses and the bacteria, but it's also harmful to normal cells. And then with COVID-19, too often we get an out-of-control inflammation that can result in a cytokine storm, hyperinflammation. So the cytokine storm can actually be treated with antibodies against the spike protein, as well as against the IL-6 cytokine to prevent the cytokine storm. So stem cells have also been used against cytokine storm. Umbilical cord stem cells have shown to reduce cytokine storm in COVID-19 patients, increasing survival from 42% to 91%. These are obviously the severely at-risk COVID-19 patients. Now, there's also a receptor that we have on our bodies, and other than the ACE2 receptor that can be attached to by the spike protein on the COVID-19 virus, and this is the TLR4 receptor, which is on many of the organs of our bodies, especially in the digestive system and so forth. And we get people suffering from obesity or tobacco smokers or even a result of aging, the TLR4 four receptors become more prominent and there gets to be more of the TLR4 receptors in those conditions. And why is COVID-19 so serious, so much more serious in the United States than in a lot of third world countries? Well, the United States has a lot more obesity than a lot of these third world countries, and we have a much older population than a lot of these third world countries, and they're tobacco smokers. Some people can't even afford to smoke tobacco in many of these countries. So anyway, I should speak about what recombinant DNA, what's that? It's DNA created by combining DNA from two different sources. And they could be completely different organisms, or one of the sources could be completely artificial. The first commercial recombinant DNA product was a transfer of human insulin-producing gene to bacteria, so that the bacteria could make insulin to treat diabetes. So before that, diabetic patients had to use insulin taken from pigs or cattle, which wasn't very good. Actually wasn't as good as human insulin, and was more costly, and actually sometimes caused reactions, inflammatory reactions and so forth. Anyway, now bacteria are used to produce the growth hormones, therapeutic cytokines, and so forth, aside from the insulin. But this is an example, a wonderful example of how GMOs, genetically modified organisms, are of tremendous benefit for humanity. So a human recombinant form of the soluble ACE2 has been tested on human patients. The COVID virus can attach to soluble ACE2 rather than to cells, and so acting as a decoy. And so this is in tests of some patients. One day after administration of this recombinant ACE2, the viral count dropped to very, very low levels because it was all being decoyed away by these soluble ACE2 recombinant molecules. So there's a technology called RNA interference, a biotechnology tool that blocks DNA from being translated. And SARS-CoV-2, the COVID-19 virus, is made up of a single stranded RNA molecule. So the RNA interference can be used against this COVID virus, and it's to prevent translation of the virus. And so here's a paper indicating its use for that effect, but hasn't been in clinical trials. Anyway, now how are we going to get this RNA of various kinds into cells? We can use liposomes, because cell membranes are lipid bilayers, and liposomes are basically lipid bilayers. And these synthetic lipid bilayers, and they can be protected from the immune system clearance by using polymers of polyethylene glycol, and that's called pegylation of the liposomes. And so the liposomes then can, to get their contents, their RNA into the cells, they can fuse with the cell membranes and reduce their RNA. And so the vaccines that are authorized, there's 2 vaccines authorized for use in the USA against COVID-19, and they both use pegylated liposomes or pegylated liposomes. Anyway, vaccines from Moderna and Pfizer-BioNTech are the 2 FDA-approved vaccines for use in the United States. And here is indicated, it uses a modified RNA in the lipid nanoparticle. And what this modified RNA does, it gets into cells from the lipid bilayer. All it does is the RNA does one thing, and that is it manufactures the spike proteins instead of the whole virus. And these spike proteins end up getting displayed on the cell surface, and then that there gets to be an antibody reaction to these spike proteins. And so if the virus then enters the body, we already have, our immune system already has all these antibodies ready to attack the viruses, the spike proteins on the viruses. So both of, as I say, both of these vaccines use this modified RNA, and but to protect the lipid nanoparticles, they require low temperatures. Moderna requires minus 20 degrees Celsius, and the Pfizer BioNTech product requires what's essentially nearly dry ice temperature, or basically typically stored in dry ice. So the cells absorb the as I say, the cells manufacture the spikes. The spikes are displayed on the cell surfaces, and they activate the immune systems by the T cells and B cells, as I described previously. So let me mention gene therapy. Gene therapy takes advantage of the ability of virus to deliver DNA or RNA to cells. We know all too well that viruses are very efficient delivering their DNA or RNA to cells. And but for gene therapy, we try to use viruses that don't cause much of an immune response. And so replace the virus DNA with some therapeutic DNA or RNA, and then use the virus to enter the cells. It's been used to correct a gene that causes blindness, for example. Children born with immune deficiency disease, these bubble babies have been cured of their immune system problems using gene therapy. So the AstraZeneca product vaccine, which hasn't yet been approved in the United States, uses a gene therapy approach. It uses a weakened adenovirus to deliver genes that encode the virus spike protein to induce an immune response. Now, the Moderna Pfizer product is about 90% effective, but the AstraZeneca product is only 62 to 70% effective. But it's been approved in the UK, Mexico, and India, and elsewhere, because it doesn't require these low temperatures for storage. It's better than nothing for sure, as far as providing an immune response, and they only require refrigerator temperatures to be stored. And they don't have much dry ice in India or Mexico or a lot of these other countries that are approving it for use. Now, the Chinese vaccine uses a very, very traditional approach, namely inactivate the virus, and which basically knock out the genes, the RNA inside the virus, but leave the spikes in place, and then just inject the inactivated virus into the patient. So the spike protein is still there. It still activates the immune system. So this is a very traditional kind of approach. The polio and rabies vaccines that have been used for a long time use the same approach, inactivated virus. And the Russian COVID-19 virus uses more of a gene therapy approach. It uses weakened adenovirus to deliver genes that code for this virus spike protein to induce the immune response. And it's been released for use before the phase 3 clinical trials aren't even expected to be completed until May of 2021, but they felt the urgency of use allowed for it to be released before these trials were completed. So the general public had access to it from January 2021. So the original virus from China didn't likely come from a laboratory, as some suspect. It likely didn't come directly from bats either. It probably came indirectly from bats and through some other animal and then into humans, but the details are not understood. But the current virus that's plaguing the world today is not the original virus from China. It's a mutation called D614G. And as you can see from this chart here, in between February and March, and after that, it just started becoming the predominant mutation of COVID virus in the whole world. The UK actually recently had a new mutation, which is even more contagious than D614G. It's not more deadly, but it's more contagious. And then there's another mutation from South Africa that's arisen. It's also more contagious and causes more serious symptoms. But none of these mutations so far have reduced the effectiveness of vaccines. Now, there's also a chemical called remdesivir, and it's administered by injection, and it interferes with the enzyme that the COVID-19 uses to replicate the RNA in cells. And it can reduce the median recovery time for a COVID patient from 15 days to 11 days. Now, the Nobel Prize in Chemistry was won by these two beautiful ladies, Emmanuelle Charpentier and Jennifer Doudna. This is the 2020 Nobel Prize in Chemistry for an adaptation of CRISPR for gene editing. CRISPR is the greatest breakthrough in biotechnology of the 21st century. I think we all agree, or it's widely agreed by scientists. And it's an acronym for a long, confusing name, which I won't try to explain, but I will try to explain how CRISPR works with many illustrations. I'm going to bombard you with illustrations about how CRISPR works. So Jennifer Doudna was trying to understand why so many bacteria have sequences of spacers, and repeats in their DNA. So her research team discovered that the spacers match portions of DNA to which the bacteria had become immune. And these spacers and repeats are a CRISPR array for the adaptive immunity of the bacteria. And alongside that, they're connected to these Cas genes. And the Cas genes control the incorporation of spacers into CRISPR array and other aspects of the CRISPR immune system. Now, one important Cas gene, Cas9, is an enzyme that can cut invading virus DNA to pieces, or at least into one piece or many pieces. One piece in the case of Cas9. There's other Cases that chop it up into many pieces. Anyway, here's how there's an example of the bacteria virus injecting its DNA into the cell, and it gets incorporated into the spacer. And then when the virus attacks again, the Cas genes cause this creation of an RNA that and the CRISPR and the spacer attached to a guide RNA, which leads it to interfere with the functioning of the virus and targets for destruction. Now, part of how this works is that DNA and RNA tend to be very similar, and they have a weak attractive force for each other. So this attractive force will allow the bacterial RNA to find matching sequences, the guide RNA in the bacteria to find matching sequences of the viral RNA for the Cas enzyme to cut. So this is an illustration of the whole process, the bacteria portions and being used to create the spacers and of the DNA and then the reaction of the of the bacteria when another invasion occurs. And this is a detailed illustration showing the same process. I told you I'd be showing lots of illustrations to emphasize my point. So actually, what did Doudna and Charpentier do to get the Nobel Prize? I guess their biggest breakthrough was they used recombinant technology to design a guide RNA that could be used to direct the Cas enzyme to any desired DNA section. So instead of the guide RNA just looking for pieces of the segments of DNA similar to what was in the spacers, now they can find any section of DNA anywhere on the whole genome. So this is a much broader application, a very powerful application. So here's another illustration of that work showing the guide RNA going up to some double-stranded DNA and having a Cas enzyme cut the DNA at the desired location. And this is another illustration of the same process. And actually, after you've cut the DNA, you can actually have a template in place to be inserted where you've made the cut, where the enzyme has made the cut. And so this is a powerful tool for adding new genes to adding new genes. You can just by simply making a cut and repairing where you've made the cut, you can also delete genes. And you can, as I said in the previous slide, insert genes by the mechanism I showed. And now, how is the most common way for diagnosing COVID-19 is using PCR, a polymerase chain reaction. And so, as I mentioned, the COVID-19 virus is an RNA virus, not a DNA virus. So the first step is to use reverse transcriptase to make DNA from the COVID-19 RNA virus, and then to use the reverse transcriptase PCR to detect the COVID-19 virus. So how does PCR work? It uses a double-stranded DNA gets denatured by heating to fairly high temperature, just below boiling point. Then it gets cooled down to be annealed, and then they use a primer to duplicate the DNA strands, and then we do this for many cycles, and we get a large enough sample of the DNA molecules to test. So CRISPR has been used for COVID-19 diagnosis. The PCR method is very slow and expensive for COVID-19 diagnosis. It requires a big laboratory, lots of equipment and so forth. And Jennifer Doudna co-founded a biotechnology laboratory that used CRISPR for a more rapid and less expensive diagnosis of COVID-19. So a CRISPR diagnosis of 36 patients with COVID-19 and 42 patients with other respiratory infections showed 95% positive and 100% negative agreement with the RT-PCR diagnosis. And it took less than 40 minutes. So I don't know. Anyway, hopefully we'll be able to use this in airports pretty soon. Anyway, George Church is another big towering figure and what may be the most famous geneticist in the world. And his institute did CRISPR gene editing research on animals and human cells, for which they filed a patent. And whereas Doudna's research team did CRISPR gene editing research on bacteria, and they filed a patent. So there was a patent dispute on the CRISPR technology. So Doudna's team was claiming that the application of CRISPR to bacterial organisms was obvious, whereas Church's team was saying that that the research on animals and human cells is what their patent covers, and not Duda's. Anyway, so the court battle began in 2016, and it continued right up to the present year. And it looks like the courts are leaning in the favor of Church's team for application to animals and humans, even though Duda's team may have claim to some of the CRISPR tools. And I don't have any more recent news than the September 2020 news that I saw. Anyway, the CRISPR can be used to destroy the COVID-19 virus in cell cultures. It has been used. And so it's used as a gene therapy technology, delivering the CRISPR CRISPR components to the cells. And whereas George Church didn't use CRISPR to attack the COVID-19 virus, when the ACE2 SARS-CoV-2 complex gets into the human cells, he just uses protein destroying mechanisms normal protein destroying mechanisms to have them chewed up by the proteasome. So, but George Church wants to use CRISPR gene editing to make all organisms immune to all possible viruses, which is pretty ambitious and pretty ambitious goal. And he also wants to make pig organs human compatible with no immune system rejection, so they can be used for human organ transplant. And he's working to use CRISPR to reverse aging. So gene therapy, as I say, it uses a modified virus to deliver genes, but these modified viruses can cause immune system reactions. And viruses often don't have the capacity to carry all the DNA and RNA required for CRISPR-Cas9 delivery. They tend to be pretty limited in size, what the viruses can carry. And so a cationic polymer has been used to deliver CRISPR components. Another mode of delivery for CRISPR-Cas9 components is electroporation. And that's the brief application of an electric field to create pores in cell membranes. And then the components can enter cells while the pores are open. And it's been used for editing the genome of induced pluripotent stem cells. Now, a couple of other therapeutics, possible therapeutics for CRISPR-Cas9. It could be used to kill antibiotic-resistant bacteria. And it could also be used to eradicate latent viruses that just get in the body and just stay there and can't currently be eliminated. So research is going on to accomplish this. Not yet successful, unfortunately, but anyway. So a big black eye for CRISPR gene editing has been the gene editing of human embryos, which was done in China to edit a gene on human embryos to prevent HIV. And the woman who gave birth to these embryos gave birth to twin girls, and this was strongly condemned by scientists all over the world. And there's also a risk that deleting the CCR gene could increase the risk for West Nile virus, but that doesn't occur very often in Asia. So that's really not a strong argument against it. The main argument is it's a bad idea. Most scientists just don't like the idea of editing human embryos. So stem cells, they're they normally heal wounds. We've got a lot of stem cells in our body that replace our red blood cells every 4 months, or skin cells every month, and the linings of our intestine every few days. And the somatic stem cells are particular to the tissues in which they reside. But the embryonic stem cells could give rise to stem cells for any tissue, and therefore have a great potential for regenerative medicine. And induced pluripotent stem cells are stem cells created by from somatic cells. For example, skin cells, or just any normal cell in our body, and they're similar to embryonic stem cells in their capacity to produce stem cells for any tissue, but they're more vulnerable to cancer. So how are embryonic stem cells produced? Well, they come from blastocysts. So when an egg is fertilized, it migrates down the oviduct and eventually develops into a blastocyst, and that gets implanted into the uterus, and which is number 4 in this illustration here. So so it's possible just to take some of these embryonic stem cells from the blastocysts, these green things shown here in the illustration, from the inner cell of the blastocyst, and then they can be cultured and used. But induced pluripotent stem cells, as I say, can come from any cell of the body, and they get reverted by using these transcription factors that I show up in the upper left there. These transcription factors, these factors can be added to these normal skin cells and so forth to make them revert back to resemble embryonic stem cells. And so essentially you're getting stem cells without having to go back to embryos, which a lot of ethicists don't think is a bad idea. So organ and tissue transplants either fail due to immune reactions or require drugs to suppress the immune system. So embryonic or induced pluripotent stem cells could potentially recreate any organ or tissue and cure many diseases like diabetes, Alzheimer's disease, and so forth. And skin cells in patients with macular degeneration have been used to create retinal cells, which were transplanted, resulting in the halting of the degeneration and improved vision. And we can also create organoids from induced pluripotent stem cells. Organoids are artificially grown masses of cells that resemble an organ. So they can be created from iPSs from a patient with a disease to study the disease, or they can be used to grow tissue outside of a patient for transplant in the patient to replace damaged tissue. So here's the example of a cancer application of organoids. We got normal tissue organoids taken from normal tissue, or we can take we can create organoids from tumor tissue to study what the particular, because cancer cells can be very different in different patients, and so it's good to be able to just go into the patient, take a sample of the cancer cells and study them by creating organoids. So here's this example of the process. We can use either embryonic stem cells or induced pluripotent stem cells to create these organoids. And in this case, it's showing brain organoids. So we can create brain tissue and study neurodegenerative diseases like Alzheimer's diseases, and test potential therapies on these organoids without having to test them on the patients themselves. So it's also been used to study COVID-19. And the induced pluripotent stem cells derived from organoids have demonstrated the capacity of SARS-CoV-2 to infect brain tissue. And transgenic mice are mice that these transgenic mice mice normally have ACE2 receptors, but they don't they don't function the way human ACE2 receptors are. So anyway, they used transgenic mice infected with the COVID-19 virus who died from the virus, the study showed that the mice died from the virus in the brain, not from virus in the lung. So it wasn't respiratory disease that killed the mice. It was the infection of the virus into the brain. And autopsies of human patients who died of COVID-19 apparently confirm the finding in the mice that what's really lethal is the COVID-19 virus in the brain, causing the most damage. So I will end on that note.
Okay. Well, great, Ben. Thank you for that comprehensive presentation. We all appreciate it. We have a couple of questions here. First, how long do you believe it will be before things get back to a more normal state with COVID-19?
Well, this is outside of the context of my presentation, but I think the vaccine certainly by the end of 2021, I think almost anybody who wants to have the vaccine will have the opportunity to get the vaccine, and I think pretty well things could. I think certainly sometime in this 2021, I think things will be getting back to normal.
I hope so. Ben, another question was, do you think that the vaccine for COVID-19 will be safe for people to take?
Well, there are many vaccines, and they have been proven to be safe. The FDA wouldn't have approved these vaccines if they weren't safe. Unfortunately, the Russians and the Chinese have brought their I don't know, fortunately or unfortunately, have brought their vaccines into use before the safety has been proven. And actually, there's recently some problems seen with the Chinese vaccine in Brazil. I saw a Wall Street Journal article on that. So I would say be hesitant about using these Chinese or Russian vaccines before the clinical trials and testing has been completed. But I think the Moderna, I definitely think the vaccines approved by the FDA in the United States are worth using, and the AstraZeneca vaccine, I think it's definitely should be, even though it's not as effective. The AstraZeneca, I mean the Moderna and the Pfizer vaccine, are over, nearly 95% effective, and very safe, and there's been a few. Some people have reactions. It's temporary, but certainly nothing worse than getting COVID-19. So I think it's a possibility you'll have some side effects, but I still think it's better to be vaccinated and safe than to not be vaccinated.
I have to agree with you, Ben. And when you look at all the hundreds of thousands of people that have gotten the vaccine, and there hasn't been any great problem, it seems. So I have to agree with you that it's going to be more important to take the vaccine than not to. Well, again, thank you for this wonderful presentation. Those are the only questions we have from our online people that are watching. I would invite anyone that has questions when we go into the recording to send those questions in to me, and I'll get with Ben to see if he has any answers for those. I want to thank you all for attending our event. And Ben, thank you very much for celebrating James Bedford Day with us. It was actually Ben that suggested that we celebrate Bedford Day, and we have now for, I guess, 5 years? I think it's been 5 years running now, so that's a fantastic thing. I'd like to invite you all now to return to the Church of Perpetual Life live stream that we'll have on January 28th. That's the fourth Thursday of the month, where we will have Bill Falloon giving an update on age reversal, and also remind you about the January 23rd event that the folks at the Radical Life Extension group are going to be having. That's the let me give you that information again. That's January 23rd, The Eyes on the Prize, The Smart Way to Stop Sickness and Stop Aging. That's hosted by James Stroll and Bernadine. If you want to sign up for that, go to the Coalition for Radical Life Extension, and you can join that free seminar as well. Thank you, Ben. Stay healthy. Stay healthy, everyone. Thank you for attending our live stream this month. Be sure to get our monthly email newsletter for updates on our next service and other updates and discoveries in age reversal technologies and health practices. Please share the recording of this event and our other events with all of the people that you care about, your family, your friends, those that you love. And join us next month for another brilliant presentation here at the Church of Perpetual Life.